and welcome to our next session here in our first chapter on motivating and introducing interpretable machine learning. So in this session here, I will discuss different aspects of interpretability and different needs, different reasons for why we might be interested in interpretable models. And it turns out there are actually quite a few very different reasons for interpretation. So the first one might be to discover and gain certain global insights for our model. So this guy here. Yeah. The second reason might be to improve, debug, and audit models. A third one might be to understand and control individual predictions. And the fourth one is heavily also associated with things like fairness and fair machine learning. So to justify certain predictions, to justify the application for certain machine learning models in applications, and to figure out whether models are really fair regarding certain individuals or certain subpopulations. So let's start with this first goal, and let's deep dive into these a little bit further. So the first thing I want to talk about here is this a goal of being able to discover and gain global insights into our model. So usually this means understanding the model as a whole on the complete input space. So this might refer to gaining insights about the data set, the underlying distribution, the relationships between the inputs and the outcome, and our model in general. So an example might be, and we're going to look at this again and again, so you might be looking at this very popular bike sharing data set here. So this is kind of, I don't know, has become something like the IRIS data set for interpretable machine learning. For this bike sharing application here, we have a certain number of features, certain amount of covariates, which, for example, measure the current temperature at a certain day, which month we are in, which season we are in, humidity, wind speed, and so on. And the goal is to predict the number of bike rentals per day at a certain bike shop. Because if we can do that, then we can kind of pre-stock, we can plan better for this application. And it's just kind of a nice toy example to study, because the idea is that we understand these relationships fairly well. We have a certain idea what should happen here, and we can check whether our interpretability techniques produce the desired result. And an example question that we might ask now against our model as a whole is, for example, which features influence model performance the most and to what extent? So here we could now compute something like a certain feature importance measurement, maybe through permutation feature importance or related technique. What that exactly means, we will study later here in the lecture. But this might give us something like a quantitative outcome, like visualized here in this plot, which would tell us that the year and the temperature are the most important features. So these guys, because we have some numerical score associated with these features, which later on we'll learn, will tell us something like how much will model performance degrade if we would not use these features, or would destroy the contained information in these features. And there might be other features like, I don't know, this, whether it's a holiday or not, which are less important, and maybe we can drop those also from the data set. And that, of course, would be very much related also to feature selection. Then there is the area of being able to improve, debug, and audit models. So it should be hopefully somewhat obvious to you guys that if you are applying a machine learning model, I mean, you are producing a bunch of code, right? Actually, producing two pieces of code, I guess. One which learns on your data set, and then producing the implied code, like the machine learning model itself, which then predicts something. So in a certain sense, we are in the area of software engineering and programming. And then we are not only like directly producing this model, directly learning this on some given data set. I mean, there's the process of collecting the data, of cleaning the data, then using the model, evaluating it, and basically flaws and mistakes that can happen at every stage, and sometimes they're extremely hard to detect. They are this is a general problem in software engineering, that bugs can happen at any stage of a program, but in data science and machine learning, this is even more complicated, it's even it's more likely that mistakes can happen here. Just think about that. Maybe your data set that you've collected is somehow biased, or there are certain mistakes even in the data set. How are you ever going to figure this out if you have no way to peek inside of your model? And there's this cautionary tale here, which is this neural network tank example, and there's a huge discussion, and there are some very interesting blog posts and articles out which discuss whether this example has actually ever happened. Probably never has. I'm still going to explain this here a bit because it's kind of nice to explain, and I guess we'll end with a more realistic instance. We'll end with a more realistic instance of the same problem. But this cautionary tale here tells us of an example where pictures have been taken to detect whether there are tanks on these images, and then a neural network was potentially trained to detect this, based on this image data. And this obtained a very good fit on training data. But if when this model was applied to new data, I don't know, in the field, on new pictures, it drastically failed. And the idea here is that this failure actually happened because if you look at the training data, the model was not really ever focusing in and zooming in on the object which was of interest, so whether there was a tank on the picture or not. It actually turned out, in this potentially hypothetical example, that all the photos in the training set with the tanks, they only showed a cloudy sky, and the photos without the tanks showcase the sunny sky. So the pictures have been taken at just different times, maybe on different days or on different weeks with different weather conditions. And then the model basically learned, I don't know, maybe even the average gray value of the background. At different versions of this tale. Sometimes it wasn't cloudy, but it was snowy, or some other artifact was visible there on the pictures. And yes, of course, we can detect that if we apply our model to newly collected data. That's different than just doing something like a cross-validation. That wouldn't have shown us this problem here at all, because we would still have performed that based on the available data set. But if we could have peeked inside of the model and would have understood how the predictions of the model came about, we might have also had a chance to detect that. Now, as I said, it seems to be pretty likely that this exact example has never happened. But if you also look at the blog post studying that, which we have also linked here in the slides, there's an interesting comment by the guy called Thomas Dieterich. So he's a very, very famous researcher in machine learning, and he said the following. So we made exactly the same mistake in one of my projects on insect recognition. So they photographed about 50 classes of insects, and they put the specimen into different vials, and then apparently bubbles would form in the alcohol. Bubbles would form in the alcohol, different bubbles on different days. The learned classifier was surprisingly good, but the saliency map revealed. So saliency map, that would be something like an interpretable machine learning technique, revealed that it was reading the bubble patterns and ignoring the specimens. I was so embarrassed that I had made the oldest mistake in the book. Unbelievable lesson. Always randomize, even if you don't know what you're controlling for. Okay, so maybe this exact example never happened, but there are many, many, many similar instances that do happen, and where us being able to peek inside of the decision-making process of the model can potentially help to at least detect these problems. Then we still have to do something against that. For example, by randomizing. And moving more towards something like an RCT, so randomized controlled trial. And this is more kind of the data science perspective, I guess, on the problem. But there's also this, foreshadowed this already a bit, this debugging and auditing perspective from computer science, right? So already said that, I mean, we are producing computer programs if we are doing machine learning, and actually we are doing something that's even weirder and more complicated, right? So we have a program, or we write a program, and this is kind of our learning algorithm, or we call into that, and that piece of software, that program now writes automatically another piece of software automatically, which is our model, which is then potentially used in a very complicated and complex system. Yeah? So this usually is not used in isolation, but it's used in some context, which is probably also a complicated piece of software. Now, as I already said, we can try to prove correctness of programs. We can try to kind of use certain, I don't know, instruments or processes to avoid bugs in these types of programs from the outset, or prove that they are not there. But it turns out that this is rarely always possible, right? Very often the only thing that we can do is we can try to minimize the likelihood of such bugs. We can try to audit programs. How are we doing that if we cannot understand the code anymore? So if there's, I mean, that's difficult enough already, but now imagine you have a piece of code where, like, at some stage, I don't know, some input is pushed inside of a complicated, I don't know, linear algebra formula, which does the prediction of a certain neural network. How are you ever auditing and figuring out that this is bug-free and does what it should do? Do you only want to do this based on, I don't know, something like a single cross-validation score? I guess even if in such a scenario you're basically learning to predict, right? You are okay with a model that just works fairly well, and you do not necessarily need to understand that in the context of your application. Being able to interpret your model, being able to kind of validate this is always helpful. Yeah. So both of these scenarios, or sorry, both of these aspects that I just discussed, are mainly regarding being able to explain and understand the global structure of a given machine learning model. There's also the scenario of being able to understand and control individual predictions. So very often this is, very often this means explaining individual decisions. Often that means that you would like to kind of explain these individual predictions based or towards the user who provided the individual inputs, and the prediction is kind of used on top of his individual data that he provided to the system. And maybe either that user wants to, I don't know, maybe that user even has a legal right having these predictions explained back to him, or just interested in understanding how the prediction came about, or that user wants to guard against unwanted actions against him. So again, we already discussed this a little bit. Credit risk as applications might be a popular example here. So we have some customer and credit information. So for example, there's the age of the customer, the gender, the job, the amount that the customer is asking for in the credit, the duration of the credit, and so on. And then this is pushed inside of our machine learning model, and either there's a recommendation to grant the credit or reject it. So then, I mean, obvious questions are, why was my credit rejected? Is this a fair decision? I don't know. Credit applications of females rejected more often than of males. Can I change something in my data? Maybe down the line, so that my credit is accepted. Can I somehow, I don't know, change my behavior in the future, so I have a better chance of being successful in the next round, or I don't know, 10 years down the line, or maybe the applied model by the credit company is, I don't know, bullshit, and I want to be able to figure this out and maybe take legal actions against this. So for example, here we might receive something like an explanation. if the person was more skilled and the credit amount had been reduced to a lower amount, then the credit would have been granted. So that would also maybe directly give you a kind of a course of action. Yeah, you could ask for less and then be more successful. Yeah, I don't know, you study for 10 more years and I don't know, gain a PhD, and then maybe then your credit is accepted. And explanations like that we would call counterfactual explanations. We're going to study these also here in depth in this lecture. And now we come to the first and last aspect of why explanations and interpretability might be of interest to us, and this is in regard to justification and fairness. So we potentially want to investigate if and why biased, unexpected, or potentially discriminatory predictions are being made by our model. So there's already talked about this in the first session. There's this now very infamous COMPASS example. So that's an acronym that's short for Correctional Offender Management Profiling for Alternative Sanctions. So I guess I have already a hard way of pronouncing that. And that was a commercial algorithm used by judges in the United States that was really put to use to assess the defendant's likelihood of reoffending. I guess that was mainly used in regard to violent offenders who were already in jail. And then the system was tasked to predict whether there was a certain likelihood of that person to reoffend after being already in jail for a previous crime. And yeah, the model was tasked to predict kind of the level, the probability of that risk, so either high risk, medium risk, or low risk. And then this was evaluated based on a questionnaire, which had to be answered by the defendant. And then that person, or the recommendation of that system, was provided to a human judge, and the human judge then used that predicted score to form a decision whether that person should go back to jail or not. So I guess that's a really sensitive and life-changing decision, and one of these really critical applications of ML models that we discussed before. So now, if we only look at a descriptive data analysis of the outcome of the predictions of such a model, and if we only would partition these predictions into kind of two classes and analyze the score distribution on these two classes. So we might look at the subpopulation of black defendants and of white defendants, and then simply draw here as a histogram the scores of low risks to high risks. We would immediately see that the model is skewed towards predicting much lower risks, as you can see here, for white defendants than for black defendants. So there's a strong indication that the model is discriminated against black defendants, and I guess we wouldn't even potentially really need interpretable machine learning to figure this out. We could see this even just from this simple descriptive data analysis, and that's even if, and that's a very big if, this would be based on some form of, I don't know, objective evidence. And that's don't want to go into this here much further, but that's a very big if. If such a model would be applied in practice, do we really kind of want to perpetuate this situation indefinitely into the future? This would really create a very strong bias against any black defendant in the future. So this is really something that we want to guard against. At the very least, we want to make this transparent and then open this up to, I guess, public discussion if we really want to use such systems, and whether they have any kind of evidence in the real world to kind of justify their application. We definitely don't want to apply systems like these blindly, and it's now pretty obvious that this model here was faulty. So we could now use also IML techniques instead of this rather descriptive or exploratory data analysis to study the same question. So we could also now use either a feature effects or a feature importance analysis, maybe a local analysis of two exemplary observations for two exemplary defendants, Here we did this. We applied the SHAP method and we applied the LIME method. And then we could look at whether certain features now have a stronger or a less strong effect on the predicted outcome. So here we looked, for example, at the race feature, which you can see, for example, here. You can see also here, right? And you can see that has a noticeable, well, positive effect, yeah, actually. In reality, like a negative effect, I guess, in terms of its interpretation on the violence score. And this is exactly what we have seen before. Now, maybe a little bit more transparent, a little bit more visible than in the descriptive data analysis before. And we can now potentially take actions against the application of such a model. We can at least transparently discuss this and maybe get rid of this model at all and avoid its implementation in practice.